Previous class we have discussed about the one of the important qualitative property, that is osmotic pressure. So before that I have discussed about osmosis, illustration for osmosis, and reverse osmosis, and what is the condition for reverse osmosis, and one of the important application of reverse osmosis, and one more important topic, that is hypertonic solution, hypotonic solution, and isotonic solutions. So, and one more very important for 1 mark, that is what happens to size of blood cells when they are placed in the normal saline solution, that is 0.9% W by V NaCl solution is called as normal saline solution. So ಅದೇ ರೀತಿ ಬ್ಲಡ್ ಸೆಲ್ಸ್ ಅನ್ನ ನಾರ್ಮಲ್ ಸಲೈನ್ ಸೊಲ್ಯೂಷನ್ ಗಿಂತ ಜಾಸ್ತಿ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಇದ್ದಾಗ ಬ್ಲಡ್ ಸೆಲ್ಸ್ ಏನಾಗುತ್ತೆ, ಸ್ಟ್ರಿಂಕ್ ಆಗುತ್ತೆ. ಅದೇ ನಿಮಗೆ ಲೆಸ್ ದ್ಯಾನ್ 0.9% ನಾರ್ಮಲ್ ಸಲೈನ್ ಸೊಲ್ಯೂಷನ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಕಡಿಮೆ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಸೊಲ್ಯೂಷನ್ ಅಲ್ಲಿ ಬ್ಲಡ್ ಸೆಲ್ಸ್ ಇದ್ದಾಗ ಏನಾಗುತ್ತೆ, ದಟ್ ವಿಲ್ ಸ್ವೆಲ್ಸ್. So that is size of blood cells varies depending on the concentration of the saline solution. So and one more we have discussed, that is the calculation of osmotic pressure by using the formula, that is pi is equal to W2 or P into 1000 divided by M2 into V in ml. That is a very important formula to calculate the osmotic pressure. So at the same time, so I am going to discuss the one more important qualitative property. So in this session, so that is third one. So already we discussed about the RMP and also osmotic pressure, and the third qualitative property, that is what as elevation of boiling point. Elevation of boiling point. So that is indicated as delta EB, where we refer for solvent. So delta, that is a change in boiling point. So nothing but how the boiling point is elevated by adding non-volatile solute that we discussed. So before that, what is the meaning of a boiling point? So liquid and the boiling point and the so what is the meaning? So let me take a liquid here. So this is the liquid, let me say water. So when you, this is the surface of the liquid, so we'll get the vapors of the same liquid above the liquid phase. That phase is called as vapor phase, and this is the liquid phase. Now I am going to heat this liquid at a particular temperature. One particular temperature heat out. So one particular temperature, the vapor pressure of that liquid is become equal to 1 atmospheric pressure. So remember, so in the liquid, when you are going to heat the liquid, so at a particular temperature, particular temperature, so vapor pressure in liquid, the vapor pressure is equal to 1 atmospheric pressure equal. So yavaga vapor pressure of liquid 1 atmospheric pressure equal to a particular temperature we can call it as boiling point. Very simple concept. Then what is the meaning of boiling point? That is the temperature at which vapor pressure of the liquid become equal to 1 atmospheric pressure, and that particular temperature is called as boiling point of that liquid. Let me say example, that is a water. So water, we know that boiling point of the water is about 100 degrees Celsius. So at 100 degrees Celsius, what happens? The vapor pressure of the water become equal to 1 atmospheric pressure. So 1 atmospheric pressure also say in bar, that is 1.013 bar. As equal right? So E one particular temperature we can call it as boiling point of the water. Okay. So then what is the meaning of boiling point? The boiling point is the temperature. It is the temperature at which vapor pressure of liquid become equal to 1 atmospheric pressure. Become equal to 1 atmospheric pressure. That temperature is called as boiling point of that liquid. So now, so how the boiling point of the solvent or water, say example water, is elevated. Elevation of boiling point. So when they consider the solvent, to the solvent I am going to add a solute, non-volatile solute. Solute niಮಗೆ solvent to boiling point ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ಆಗುತ್ತೆ. That is the meaning elevation of the boiling point. So why the boiling point of the solvent is increases by adding a solute, or slightly elevated by adding non-volatile solute. That we have to explain. That is the concept elevation of the boiling point. So that is explained by taking illustration. So let me take a beaker here. So in this beaker, I am going to take a pure solvent. So here there is no solute. So this is the surface of the solvent. This is the solvent here. So this is the volatile solvent. So therefore, volatile will get the vapors of that solvent above the liquid surface. So that is the vapor pressure of the pure solvent is considered as a P0. Already in the previous classes I said P0 is the vapor pressure of a pure solvent. So in non marketing, right? So let me start with this heating this pure solvent. This solvent heat must start marketing. So solvent heat pump right? ಯಾವುದೋ particular temperature ಅಲ್ಲಿ the vapor pressure ಈಗ ನೀವು heat ಮಾಡಿದ್ರೆ vapors ಜಾಸ್ತಿ ಆಗ್ತವೆ. So ಆ vapor pressure of pure solvent ಏನು ತಗೊಂಡಿದ್ದೀನಿ P0 ಅಂತ ತಗೊಂಡಿದ್ದೀನಿ. So ಯಾವುದೋ ಒಂದು particular temperature ಏನಾಗುತ್ತೆ the vapor pressure of that solvent of pure solvent become equal to 1 atmospheric pressure. ಯಾವಾಗ vapor pressure of pure solvent ನಿಮಗೆ 1 atmosphere equal ಆಗುತ್ತೋ ಆ particular temperature ನ we can call it as a boiling point of the pure solvent. The boiling point of the pure solvent is taken as T0B ಅಂತ ತಗೊಂಡಿದ್ದೀವಿ. So that is taken as T0B, where B refer for boiling, not in the use market that is pure solvent. So that is T0B is the pure boiling point of the pure solvent. So at the same time, so for the same solvent ಇನ್ನೊಂದು ಬಿಕಲ್ ತಗೊಂತಾ ಇದ್ದೀನಿ. So same solvent ಇಲ್ಲಿ ತಗೊಂಡಿದ್ದೀನಿ. So to this solvent I am going to add a non-volatile solute. A non-volatile solute. So this is the surface of the solvent. So what happens when the non-volatile solute reacts with solvent, that is become a solution. That is a homogeneous mixture. So remember the solute is non-volatile solute and the solvent is solution. So what happens when the non-volatile solute is added to solvent, already explained in one of the previous class, that some of the solute particles are replaces the solvent molecules on the surface. Surface is solvent molecules. When we add non-volatile solute into the solvent, what happens? The number of solute or some solute particles replaces the solvent molecules on the surface. And what happens? The number of water molecules or the solvent molecules which are get escape from the solution. ಅಂದ್ರೆ ಇಲ್ಲಿ ಬರ್ತಕ್ಕಂಥ ವೇಪರ್ಸ್ ಏನಾಗುತ್ತೆ ಸಾಲ್ವೆಂಟ್ ಅಂತ ಕಡಿಮೆ ಆಗುತ್ತೆ because the fraction of surface of the solvent is occupied by the or blocked for the evaporation ಆಗುತ್ತೆ ಬ್ಲಾಕ್ ಆಗುತ್ತೆ. ಸೊ ಇಲ್ಲಿ ಬರ್ತಕ್ಕಂಥ ವೇಪರ್ ಪ್ರೆಷರ್ ಅಂತ ಹೇಳ್ತೀವಿ ವೇಪರ್ ಪ್ರೆಷರ್ ಆಫ್ ಸೊಲ್ಯೂಷನ್ that is taken as P ಅಂತ ತಗೊಂತೀವಿ. ಸೊ ಈಗ ಈ ವೇಪರ್ ಪ್ರೆಷರ್ ಆಲ್ರೆಡಿ ಹೇಳಿದ್ದೀನಿ ಪ್ರೀವಿಯಸ್ ಕ್ಲಾಸ್ ಅಲ್ಲಿ ವೇಪರ್ ಪ್ರೆಷರ್ ಆಫ್ ದ ಸೊಲ್ಯೂಷನ್ is lesser compared to vapor pressure of pure solvent. ಯಾಕೆ when we add non-volatile solute, some of the solute molecules are occupies the fraction of surface, so that the fraction of surface is blocked for the evaporation. So at the same time, now I am going to heat this solution. Solution heat ಮಾಡ್ತಾ ಹೋಗ್ತೀನಿ. ಯಾವುದೋ ಒಂದು particular temperature ಅಲ್ಲಿ again ಏನಾಗುತ್ತೆ the vapor pressure of the solution become equal to 1 atmospheric pressure. Now the temperature is called as a boiling point of the solution. So ಇಲ್ಲಿ ತಗೊಂತಾ ಇರೋದು pure solvent, ಇಲ್ಲಿ ತಗೊಂತಾ ಇರೋದು solution. So ಈಗ ಇಲ್ಲಿ ಯಾವುದೋ ಒಂದು particular temperature ಯಾವ ತಗೊಂಡಿದ್ದೀವಿ T0B is the boiling point of pure solvent. At this temperature the vapor pressure of the pure solvent become equal to 1 atmospheric pressure. Therefore T0B is called as the boiling point of pure solvent. Now so at a particular temperature what happens here there is a solution, the vapor pressure of the solution become equal to 1 atmospheric pressure. Now the temperature is taken as boiling point of the solution, that is taken as TB, where T0B is the boiling point of pure solvent, where TB is the boiling point of solution. So now, so ಈಗ ನಾವು observe ಮಾಡಬೇಕು what happens T0B and TB. T0B ಗೆ ಕಂಪೇರ್ ಮಾಡಿದಾಗ TB ವ್ಯಾಲ್ಯೂ ಜಾಸ್ತಿ ಆಗುತ್ತಾ ಕಡಿಮೆ ಆಗುತ್ತಾ ಅಂದ್ರೆ ಪ್ಯೂರ್ ಸಾಲ್ವೆಂಟ್ ಗೆ ಕಂಪೇರ್ ಮಾಡಿದಾಗ ಸೊ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಆಫ್ ಸೊಲ್ಯೂಷನ್ ಜಾಸ್ತಿನ ಅಥವಾ ಕಡಿಮೆನಾ, ಸೊ ದಟ್ ಯು ಹ್ಯಾವ್ ಟು ಡಿಸ್ಕಸ್. ಸೊ ಬಿಫೋರ್ ದಟ್ ಸೊ ಐ ಆಮ್ ಗೋಯಿಂಗ್ ಟು ಕಂಪೇರ್ ದ ವೇಪರ್ ಪ್ರೆಷರ್ ಆಫ್ ದ pure solvent and the solution. Already we know that vapor pressure of the solution is always greater than the vapor pressure of the pure solvent. Athwa vapor pressure of pure solvent is higher always than that of the vapor pressure of solution. And also I already said in one of the previous class, the vapor pressure is inversely proportional to boiling point. Please remember this relationship. Vapor pressure is inversely proportional to boiling point. Already explained in the previous classes. So here, so P naught is P is less than P naught andaga. That is vapor pressure of solution is less than that of the vapor pressure of a pure solvent andmele. So ನಾವೇನು ಹೇಳ್ಬೋದು vapor pressure ಕಡಿಮೆ ಇದೆ ಅಂದ್ಮೇಲೆ boiling point ಏನಾಗಿರಬೇಕು ಜಾಸ್ತಿ ಇರಬೇಕು. So therefore you can say so TB, that is the boiling point of the solution is higher than that of the boiling point of the pure solvent. This is a very important. TB is greater than always than that of the T naught B. The reason is one way when we add non-volatile solute into the pure solvent, that is become a solution. So that what happens, the vapor pressure decreases. So because the fraction of surface is black for evaporation, since the vapor pressure decreases, to make it as equal to 1 atmospheric pressure, it requires a high temperature compared to pure solvent. Pure solvent boil ಆಗ್ತಿರೋದು T naught B ನಲ್ಲಿ. ಯಾಕಂದ್ರೆ vapor pressure equal to 1 atmospheric pressure ಆಗಿದೆ. ಇಲ್ಲಿ 1 atmospheric pressure ಗೆ solution equal ಮಾಡಬೇಕು ಅಂದ್ರೆ ಅಲ್ಲಿ evaporation ಕಡಿಮೆ ಆಗಿದೆ because due to presence of non-volatile solute. So aವಾಗ so TB ಅನ್ನೋದು somewhat higher compared to that of the T naught B. ಯಾಕಂದ್ರೆ ವೇಪರ್ ಪ್ರೆಷರ್ ನ ಜಾಸ್ತಿ ಮಾಡಬೇಕಂದ್ರೆ ವೇಪರ್ ಪ್ರೆಷರ್ ಜಾಸ್ತಿ ಮಾಡಬೇಕು ಅಂದ್ರೆ you have to raise the temperature, boiling point ಅನ್ನು ಸ್ವಲ್ಪ ಏನಾಗಬೇಕು ಜಾಸ್ತಿ ಆಗಬೇಕು. So therefore TB is always greater than that of the T naught B. Reason ಕೊಡಬೇಕಾದ್ರೆ so that is when we add non-volatile solute, what happens? The vapor pressure of solution decreases. Vapor pressure of solution decreases. ಈಗ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ನಾವು ಚೆಕ್ ಮಾಡಬೇಕು ಅಂದಾಗ ವೇಪರ್ ಪ್ರೆಷರ್ ಆಫ್ ಸೊಲ್ಯೂಷನ್ ಕಡಿಮೆ ಆಯ್ತು ಅಂದ್ಮೇಲೆ ಬಟ್ ಅದು ಏನಕ್ಕೆ ಈಕ್ವಲ್ ಆಗಬೇಕು 1 atmosphere ಈಕ್ವಲ್ ಮಾಡಬೇಕು. ಆ ಈಕ್ವಲ್ ಆದಾಗ ಮಾತ್ರ ಅದನ್ನ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಅಂತ ಹೇಳ್ತೀವಿ. ಬಟ್ ಇಲ್ಲಿ ಏನಾಗಿದೆ ವೇಪರ್ ಕಡಿಮೆ ಆಗಿದೆ. ಸೊ ದಟ್ high temperature that is greater than boiling point of pure solvent. Pure solvent ಗಿಂತ ಜಾಸ್ತಿ ಇರಬೇಕು. That is the high temperature that is greater than boiling point of solvent required to make the vapor pressure of solution equal to 1 atmospheric pressure. So ಅಲ್ಲಿ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳಿ pure solvent ಅಲ್ಲಿ T naught B ಇದೆ. When we add non-volatile solute, what happens? The vapor pressure decreases. Vapor pressure ಕಡಿಮೆ ಆಯ್ತು ಅಂದ್ರೆ ಈಗ ಕಡಿಮೆ ಆಗಿದ್ರೆ ಮತ್ತೆ ಇದು ಜಾಸ್ತಿ ಆಗಬೇಕು ಅಂದ್ರೆ ಆ ಟೆಂಪರೇಚರ್ ಗಿಂತ ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ಟೆಂಪರೇಚರ್ ಏನಾಗಬೇಕು ಬಾಯ್ಲ್ ಆಗಬೇಕು. ಸೊ therefore at that temperature again ಏನಾಗುತ್ತೆ boiling point vapor pressure equal to 1 atmospheric pressure. ಇಲ್ಲಿ ಒಂದು ಸಿಂಪಲ್ ಕ್ವೆಶ್ಚನ್ ಕೇಳ್ತಾನೆ, what happens the boiling point of solvent when we add a non-volatile solute in it ಅಂತ ಹೇಳ್ತಾರೆ. ಅಂದ್ರೆ non-volatile solute ಅನ್ನು ಅದಕ್ಕೆ ಆಡ್ ಮಾಡಿದಾಗ solvent ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಏನಾಗುತ್ತೆ. So that is easy to remember. ಇಲ್ಲೇ ಹೇಳ್ತೀನಿ elevation of boiling point. When we add non-volatile solute into the solvent, definitely the boiling point is elevated. ಯಾಕೆ ಅಂತಂದ್ರೆ by adding non-volatile solute, what happens? The vapor pressure of solution decreases. Therefore, the temperature that is greater than boiling point of pure solvent required. So to make the vapor pressure of solution equal to 1 atmospheric pressure. So that's why always the boiling point of the solution is greater than the boiling point of pure solvent ಅಂತ ಹೇಳ್ತೀವಿ. So let me take simple example. Illustration ತಗೊಳ್ತೀನಿ. So ಈ ವಾಟರ್ ಅಂತ ಇಟ್ಕೊಳ್ಳೋಣ. ವಾಟರ್ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಎಷ್ಟು ಬರುತ್ತೆ? let us take 100 degree Celsius. ಅಂದ್ರೆ 100 degree Celsius ಅಲ್ಲಿ ಅದರ ಒಂದು ವೇಪರ್ ಪ್ರೆಷರ್ ಯಾವುದು ಈಕ್ವಲ್ ಆಗಿರುತ್ತೆ 1 atmospheric pressure ಈಕ್ವಲ್ ಆಗುತ್ತೆ. ಸೊ ಅದೇ ವಾಟರ್ ನಾನು ಏನು ಮಾಡ್ತೀನಿ non-volatile solute ಸಮಥಿಂಗ್ x ಅಂತ ಇಟ್ಕೊಳ್ಳಿ non-volatile solute ಅನ್ನು ಆಡ್ ಮಾಡ್ತೀನಿ. ಸೊ ಆಗ ಅದು ವೇಪರ್ ಪ್ರೆಷರ್ ಕಡಿಮೆ ಆಗುತ್ತೆ. therefore the boiling point ಏನಾಗಬೇಕು ರೈಸ್ ಆಗಬೇಕು. So let me take in this solution, so water boils at about 100.5 degrees Celsius. So ಈಗ 100.5 degrees Celsius ಅಲ್ಲಿ ಅದೇ ವಾಟರ್ ಸೊಲ್ಯೂಷನ್ ಅಲ್ಲಿ ಬಾಯ್ಲ್ ಆಗ್ತಾ ಇದೆ. ಅದೇ ಪ್ಯೂರ್ ವಾಟರ್ ಎಲ್ಲ ಆಗ್ತಾ ಇದೆ 100 degrees Celsius ಆಗ್ತಾ ಇದೆ. ಅಂದ್ರೆ ಎಷ್ಟು ನಿಮಗೆ ಎಲಿವೇಟ್ ಆಯಿತು. So elevation of boiling point ನಾನು ತಗೊಂತೀನಿ. That is delta TB is equal to that is ಎಷ್ಟು ಎಲಿವೇಶನ್ ಆಗಿದೆ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಅಲ್ಲಿ. ಸೊ ಯಾವ ಜಾಸ್ತಿ ಇರೋದು that is boiling point of solution. So boiling point of solution is taken as TB. So boiling point of pure solvent that is taken as T naught B. ಎಷ್ಟು ಎಲಿವೇಟ್ ಆಗಿದೆ ಅನ್ನೋದಕ್ಕೆ ಚೆಕ್ ಮಾಡಬೇಕಾದ್ರೆ that is taken as the difference. That is delta TB is equal to TB minus T naught B. Elevation of boiling point of solvent is equal to difference in the boiling point of solution and boiling point of pure solvent. That is called as delta TB. So let me check. So in the given example, TB is the boiling point of a solution. Yesterday 100.5 degrees Celsius. minus what is the T naught B? What is the pure solvent to boiling point temperature? That is about 100 degrees Celsius. That is equal to 0.5 degrees Celsius. That is the boiling point elevation. 0.5 degrees Celsius to boiling point rise agide ಅಥವಾ elevate agide. That is the meaning elevation of boiling point. So when we add non-volatile solute into the solvent, definitely the vapor pressure of the solution decreases. We know that vapor pressure is inversely proportional to boiling point. As the vapor pressure of solution decreases, to make it as equal to 1 atmospheric pressure, we require the high boiling point. So therefore, somewhat a high boiling point is required to make the vapor pressure equal to 1 atmospheric pressure in the solution. Hence, always TB, boiling point of solution is always higher than that of the boiling point of pure solvent. ಎಷ್ಟು ಟೆಂಪರೇಚರ್ ಜಾಸ್ತಿ ಆಯಿತು ಅಂದ್ರೆ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಎಷ್ಟು ಎಲಿವೇಟ್ ಆಯಿತು, that can be calculated delta T is equal to TB minus T naught B. This is a very important equation for problems. And TB is example ಅಲ್ಲಿ ತಗೊಂಡಿರೋದು 100.5 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ ಇದೆ. ಅದೇ ವಾಟರ್ ನಮಗೆ ಪ್ಯೂರ್ ವಾಟರ್ ಆದ್ರೆ 100 ಅಲ್ಲಿ ಬಾಯ್ಲ್ ಆಗುತ್ತೆ. ಅದಕ್ಕೆ ವೋಲ್ಟೇಜ್ ನಾನ್ ವೋಲ್ಟೇಜ್ ಸಲ್ಯೂಟ್ ಇದೆ ಅಂತಂದಾಗ ಒಂದು ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ಆಗಿದೆ. ಎಷ್ಟಲ್ಲಿ ಬಾಯ್ಲ್ ಆಗ್ತಾ ಇದೆ? 100.5 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ ಅಲ್ಲಿ ಬಾಯ್ಲ್ ಆಗ್ತಾ ಇದೆ. ಯಾಕೆ ಅಂದ್ರೆ ಸಲ್ಯೂಟ್ ಕ್ಯಾನ್ ಡಿಕ್ರೀಸಸ್ ದ ವೇಪರ್ ಪ್ರೆಷರ್. So therefore, minus 100 degrees Celsius modulate will get 0.5. This 0.5 degrees Celsius is the elevation of boiling point. So why it is occurs? Because due to addition of non-volatile solute, or due to presence of non-volatile solute. So one mark only, what happens the vapor pressure of solution by adding solution, solve non-volatile solute, that is decreases. What happens the boiling point of solution by adding non-volatile solute? That is elevated, that is increases. That is the concept of elevation of boiling point of the solvent. And this is a very important equation. That is delta TB is equal to TB minus T naught B. TB is the boiling point of solution. T naught B is the boiling point of pure solvent. So how to define the elevation of boiling point? That is a difference between the boiling point of solution and the boiling point of pure solvent is called as elevation of boiling point of solvent. ಯಾಕೆ ಎಲಿವೇಟ್ ಆಗುತ್ತೆ ಅಂದ್ರೆ because due to presence of non-volatile solute, what happens the vapor pressure that will be decreases, hence the boiling point of the solution increases compared to pure solvent. So that's about the concept of elevation of boiling point of solvent. So that can be represented by using the graph. So graph ಅಲ್ಲಿ representation ಮಾಡಬಹುದು. So ಯಾವ ರೀತಿ ಮಾಡೋಣ? So let me take a graphical representation. So in the y-axis, this is taken as x-axis in the y-axis. In the y-axis, I am going to take the vapor pressure. In the x-axis, I am going to take the temperature, that is in Kelvin. So here, this is the 1 atmospheric pressure. This is 1 atmospheric pressure. Now I am going to draw the graph. Vapor pressure versus temperature for both solvent as well as the solution. First, I am going to draw the graphical representation of vapor pressure versus temperature for pure solvent. So, as the temperature increases, if the heat more number of vapors will come over the solvent. Solvent ಮೇಲೆ ಬರ್ತಾ ಇರುತ್ತೆ vapors. ಆ vapors ಯಾವ ಒಂದು particular temperature ಏನಾಗುತ್ತೆ, that vapor pressure is equal to 1 atmospheric pressure. ಈಗ ಅಂದ್ರೆ temperature ಜಾಸ್ತಿ ಮಾಡಿದಂಗೆ vapor pressure ಏನಾಗ್ತಾ ಇರುತ್ತೆ, ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. So that is written as the temperature increases, vapor pressure also increases. So ಯಾವುದೋ ಒಂದು ಪರ್ಟಿಕ್ಯುಲರ್ ಟೆಂಪರೇಚರ್, ಆ ಟೆಂಪರೇಚರ್ ನ ಸ್ವಲ್ಪ ಅಬ್ಸರ್ವ್ ಮಾಡಿ. So this is the temperature. So on this temperature, so this is the for number 2, this is for solvent. So what happens as the temperature increases on the liquid and heat more number of vapors are come around the over the solvent. Our vapor pressure, vapor just vapor pressure also increases as the temperature increases. As the temperature increases, vapor pressure also increases. ಯಾವುದೋ ಒಂದು particular temperature ಅಲ್ಲಿ the vapor pressure of the solvent is become equal to how much? 1 atmospheric pressure. When the vapor pressure of solvent become equal to 1 atmospheric pressure, that is called as a boiling point. So ಯಾವುದು ಬರೀತಾ ಇದ್ದೀವಿ ಪ್ಯೂರ್ ಸಾಲ್ವೆಂಟ್ ಗೆ ಯಾವ ಟೆಂಪರೇಚರ್ ಈಕ್ವಲ್ ಆಗ್ತಾ ಇದೆ, ದಟ್ ಈಸ್ ದ ಟೆಂಪರೇಚರ್ ಇಸ್ ಕಾಲ್ಡ್ ಆಸ್ T naught B. That is called as T naught B. That is the boiling point of pure solvent. At this temperature, what happens? The vapor pressure of the solvent, become equal to how much? 1 atmospheric pressure. That is taken as a boiling point of pure solvent. Okay, so at the same time, I'm going to draw the graph of vapor pressure versus temperature for solution. What happens to the vapor pressure of the solution when you add the non-volatile solute? That will be decreases. ಹಂಗಾದ್ರೆ ಈ ಗ್ರಾಫ್ ಗಿಂತ ಮೇಲೆ ಬರೆಯೋಂಗಿಲ್ಲ. ನಾವೇನ್ ಮಾಡಬೇಕು, ಇಲ್ಲಿ ವೇಪರ್ ಪ್ರೆಷರ್ ಇಲ್ಲಿ ಬರ್ತಾನೆ ಸಾಲ್ವೆಂಟ್ ಅಂದ್ಮೇಲೆ 100% ಸೊಲ್ಯೂಷನ್ ವೇಪರ್ ಪ್ರೆಷರ್ ಅದಕ್ಕಿಂತ ಕಡಿಮೆ ಬರೀಬೇಕು. ಅಗೇನ್ ಅಟ್ ದ ಸೇಮ್ ಟೈಮ್ ಇನ್ ದ ಸೊಲ್ಯೂಷನ್ ನಾನು ಏನು ಮಾಡ್ತೀನಿ, ಒಂದು ಪರ್ಟಿಕ್ಯುಲರ್ ಟೈಮ್ ಹೀಟ್ ಮಾಡ್ತಾ ಹೋಗ್ತೀನಿ. ಸೊ ಆಸ್ ದ ಟೆಂಪರೇಚರ್ ಇನ್ಕ್ರೀಸಸ್ ಅಗೇನ್ ದ ವೇಪರ್ ಪ್ರೆಷರ್ goes on increases at a particular temperature. ಯಾವುದೋ ಪರ್ಟಿಕ್ಯುಲರ್ ಟೆಂಪರೇಚರ್ ಅಲ್ಲಿ, ಸೊ ಯಾವ್ದಕ್ಕಿದು, this is for solution at a particular temperature. So that is the temperature is here. So that is the temperature is called as TB. At this temperature, what happens? The vapor pressure of the solution, that is equal to 1 atmospheric pressure, and this is called as a boiling point of solution. I think it's clear. So that is, as the temperature increases, vapor pressure goes on increases. One particular temperature, at a particular temperature T naught B, the vapor pressure of solvent become equal to how much? 1 atmospheric pressure. That is called as a boiling point of pure solvent. Again, for the solution, as the temperature increases, vapor pressure goes on increases. At a particular temperature TB, the vapor pressure of the solution become equal to how much? 1 atmospheric pressure. That temperature is called as boiling point of the solution. So even you observe ಮಾಡಿ. So along the x-axis, ಹೋಗ್ತಾ x-axis ಹೋಗ್ತಾ temperature ಆಗ್ತಾ ಇರುತ್ತೆ, ರೈಸ್ ಆಗ್ತಾ ಇರುತ್ತೆ. ಇಲ್ಲಿ TB ಮತ್ತೆ T naught B observe ಮಾಡಿ. TB is here, T naught B is here, which is the higher value, that is TB. So therefore, difference na ತಗೊಂಡಾಗ, so that is taken as delta TB. So ಇಲ್ಲಿ ಬರಿಬಹುದು ನೋಡಿ ಬೇಕಾದ್ರೆ. So that is delta TB is equal to, ಯಾವ ಜಾಸ್ತಿ ವ್ಯಾಲ್ಯೂ, boiling point of solution ಜಾಸ್ತಿ ಇರುತ್ತೆ, that is TB minus T naught B. So that is the elevation of boiling point. That is the graphical representation. Okay, at the same time, for dilute solutions, the elevation of boiling point of solvent, that is delta TB, that is elevation of boiling point of solvent, is directly proportional to elevation of boiling point of solvent is directly proportional to molarity of the solution. Molarity of the solution, that is molarity. So why we are not taking the molarity? It's a very important. While explaining the concentration term in the one of the previous class, I said the molarity is the temperature dependent and it cannot be used in the experiments which involves the temperature change. And molarity is the temperature independent that can be used in the experiments that is involves the temperature change. Here there is a change in temperature, that is a boiling point is nothing but a temperature, that is changing temperature. Changing temperature also means concentration change ಆಗಬಾರದು. So therefore concentration change ಆಗಬಾರದು ಅಂದ್ರೆ concentration should be temperature independent. Therefore I am going to take the molarity here. Okay, so that is for dilute solution, delta TB, elevation of boiling point is directly proportional to molarity. Now this proportionality constant, proportionality removed by the constant, that is delta TB is equal to Kb into M. Again, it's a one more important equation. So that is what is meant by Kb. The Kb is a proportionality constant that is called as molar elevation constant. This is called as molar elevation constant, or is also called as boiling point elevation constant. Boiling point elevation constant, and also it is called as ebullioscopic constant. Ebullioscopic constant. So remember, in the study material, page number 38 ಅಲ್ಲಿ ebullioscopic ebullioscopy ಅಂತ ಆಗಿದೆ, PY ಅಂತ ಆಗಿದೆ. So make it correct. ebullioscopic ಅಂತ ಬರಬೇಕು. ebullioscopic constant or molar elevation constant ಅಥವಾ boiling point elevation constant ಅಂತ ಕರೀತೀವಿ. So again, how to define this Kb? So define Kb ಅಥವಾ molar elevation constant ಅಂತ ಕೇಳಿದಾಗ, so in the equation, let me call it as equation number 1. So I am going to take as solution molarity is equal to 1 molar. 1 molar solution to 1 molar solution is nothing but the 1 mole of solute dissolved in 1 kg of solvent. So ಯಾವಾಗ ನೀವು ಮೊಲಾರಿಟಿ 1 ಅಥವಾ 1 ಮೊಲಾಲ್ ಅಂತ ತಗೊಂತೀರೋ what happens that is Kb is equal to ಏನಾಗುತ್ತೆ ಡೆಲ್ಟಾ Tb ಆಗುತ್ತೆ. ಅಬ್ಸರ್ವ್ ಮಾಡಿ. Second m is equal to 1 molar ಅಂತ ಹೇಳಿದೀನಿ, that is the molality. So ಅಥವಾ 1 molar is nothing but 1 mole per kg. So that is Kb is equal to ಏನಾಗುತ್ತೆ ಡೆಲ್ಟಾ Tb ಆಗುತ್ತೆ. So ಅಂದ್ರೆ Kb ಅನ್ನ ಡಿಫೈನ್ ಮಾಡಬೇಕು. So ಡಿಫೈನ್ ಮಾಡಬೇಕಾದ್ರೆ ನೋಡಿ ಇದು ಕಾನ್ಸೆಪ್ಟ್ ಏನಂದ್ರೆ, so here I am going to take a 1 kg of solvent. 1 kg of solvent. To this I am going to add 1 mole of non-volatile solute. So totally we know that when the solute is added to solvent, definitely the solution vapor pressure will be decreases and the boiling point will be increases. Yes, elevate ಆಗುತ್ತೆ ಅಂತ already calculate ಮಾಡಬಹುದು. That is by using delta Tb is equal to Tb minus T0T. So ಈಗ particularly ನಾನು solvent ಎಷ್ಟು ತಗೊಂತಾ ಇದ್ದೀನಿ 1 kg ತಗೊಂತಿದ್ದೀನಿ. So ಎಷ್ಟು solute ಅನ್ನು ಆಡ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ 1 mole of solute ಅನ್ನು ಆಡ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ. So when the 1 mole of solute dissolved in 1 kg of solvent, say example water, so that solution become 1 mole of solution. The solution is 1 mole of solution. So that's the meaning 1 mole of solution is nothing but 1 mole of solute dissolved in 1 kg of solvent. ಯಾವಾಗ particularly 1 mole of solute ಅನ್ನು non-volatile solute ಅನ್ನು 1 kg of solvent ಅಲ್ಲಿ dissolve ಮಾಡ್ತೀವೋ ಅವಾಗ 100% boiling point ಏನಾಗುತ್ತೆ ಎಲಿವೇಟ್ ಆಗುತ್ತೆ. ಎಷ್ಟಾಗುತ್ತೆ that is taken as delta T. So ಯಾವಾಗ 1 mole of solute ಅನ್ನು 1 kg of solvent ಅಲ್ಲಿ particularly dissolve ಮಾಡ್ತೀವೋ ಆಗ ನಿಮಗೆ ಏನು elevation of boiling point ಆಗುತ್ತೋ that is itself called as molar elevation constant. Nothing but molar elevation constant is the elevation of boiling point when dissolving 1 mole of solute in 1 kg of solvent. Particularly 1 mole of solute ಅನ್ನು 1 kg of solute dissolve ಮಾಡಿದಾಗ ಎಷ್ಟು ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಎಲಿವೇಟ್ ಆಗುತ್ತೋ that elevation of boiling point is taken as molar elevation constant or ebullioscopic constant. I will define once again. Define Kb or define ebullioscopic constant or molar elevation constant or boiling point elevation constant. Nothing but the Kb is the elevation of boiling point of solvent observed when 1 mole of solute dissolved in 1 kg of solvent. ಅಥವಾ so 1 mole of solute ಅನ್ನು 1 kg of solvent ಅಲ್ಲಿ dissolve ಮಾಡಿದ್ರೆ ಏನು ಸಿಗುತ್ತೆ 1 mole of solution. ಅಂದ್ರೆ 1 mole of solution ಅಲ್ಲಿ ಎಷ್ಟು ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಎಲಿವೇಟ್ ಆಗಿದೆ. So again Kb defined as that is the elevation of boiling point of solvent observed in 1 mole of solution. 1 mole of solution ಅಲ್ಲಿ ಎಷ್ಟು elevation of boiling point ಆಯಿತು ಅಂತ ಚೆಕ್ ಮಾಡಿದ್ರೆ that is itself a Kb. So that's about the concept of ebullioscopic constant. And what is the unit of Kb? Kb unit ಅನ್ನು ಬರೆಯಿರಿ ಅಂತ ಕೇಳ್ತಾನೆ. So ಇಲ್ಲಿ ನಿಮಗೆ according to equation number 1, equation 1 ಪ್ರಕಾರ ಬರೀತಾ ಇದೀನಿ. So that can be written as Kb is equal to delta Tb divided by m. So what is delta Tb? Delta Tb is the elevation of boiling point. What is the unit of temperature? That is Kelvin. Delta Tb is nothing but the temperature difference. Temperature measured in Kelvin divided by what is the meaning of molarity? What is the unit of molarity? That is number of moles of solute dissolved in 1 kg of solvent. Therefore the unit is mole per kg. Mole per kg. So therefore what happens in it? Kelvin. ಇಲ್ಲಿ ಏನಾಗುತ್ತೆ kg per kg ಮೇಲೆ ಬಂದಾಗುತ್ತೆ kg ಆಗುತ್ತೆ. So mole ಮೇಲೆ ಬಂದಾಗುತ್ತೆ per mole. Very very important. That is Kelvin kg per mole is the unit of ebullioscopic constant or molar elevation constant or boiling point elevation constant. So ಅಥವಾ ಇನ್ನೊಂದು ತರ ಹೇಳ್ಬೋದು. So ಇಲ್ಲಿ ನಿಮಗೆ delta Tb ಗೆ ಅಂತ ತಗೊಂತೀವಿ that is K ಅಂತ ತಗೊಂತೀವಿ. So divided by molarity ಗೆ say molar. ಅಥವಾ ಇಲ್ಲಿ ಬರೀಬರೀಗ Kelvin per molar ಅಂತ ಬರೀಬಹುದು. Kelvin per molar. So Kelvin per molar ಅಂತ ಬರೀಬಹುದು ಅಥವಾ Kelvin kg per mole ಅಂತ ಬರೀಬಹುದು. ಯಾಕೆಂದ್ರೆ molar ಅಂತ ಏನಾಗುತ್ತೆ mole per kg. Mole per kg to the power of -1 ಅಂತ ಮಾಡ್ಕೊಂಡ್ರೆ mole to the power of -1 kg to the power of 1 ಆಗುತ್ತೆ. Again same ಆಗುತ್ತೆ Kelvin kg per mole. ಎರಡನ್ನೂ ಗೊತ್ತಿಲ್ಲ. So ಕಾಂಪಿಟೇಟಿವ್ ಎಕ್ಸಾಮ್ಸ್ ಬಗ್ಗೆ ಕೇಳಬಹುದು ಯೂನಿಟ್ ಆಫ್ Kb ebullioscopic constant is ಈ ತರ ನಾವು ಕೊಡಬಹುದು ಕಾನ್ಸೆಪ್ಟ್ ಆಪ್ಷನ್ ಅನ್ನ ಅಥವಾ Kelvin kg per mole ಅಂತ ಅದು ಕೊಡಬಹುದು. So that's about the Kb. What is the meaning of Kb and what is the unit of Kb? So the equation what becomes? So ಇಲ್ಲಿ molarity ಗೆ ನಿಮಗೆ equation ಗೊತ್ತಿದೆ. So what is the meaning of molarity? Molarity is the number of moles of solute dissolved in 1 kg of solvent. That is mass of solvent is taken as W1. 1 is referred for solvent, W is the mass that is taken in kg. But we know that number of moles of solute is nothing but mass of solute divided by molar mass of solute. That is mass of solute divided by molar mass of solute. Whole divided by W1 kg in ಬರಿಬಹುದು. W1 in grams ಅಂತ ಮಾಡ್ಕೊಂಡ್ರೆ that can be divided by 1000. So that is equal to what happens? WO2 divided by M2 into 1000 divided by WO1 in grams. That is the equation of molarity. That is already discussed in the concentration terms. Ali not better already discussed the equation with problems are marked. Ide molarity and mode, so that is substitute in the equation number 1. So what happens the equation number 1 here? Equation 1 becomes, so equation 1 becomes, that is delta TB is equal to, so that is KB into polarity formula bರುತ್ತೆ WO2 into 1000 whole divided by M2 into WO1 in grams. So what is W2 by M2? W2 by M2 is the number of moles of solute. W2 by M2 number of moles of solute is equal to W2 by M2. Hangare delta TB is proportional to W2 by M2. So that is delta TB is proportional to M2. So what is N2? Number of moles of solute. Andre delta TB is depends on the number of solute particles but not on the nature of solute particles. ನೋಡಿ ನಾನು ಹೊರಟೆ ಅಂತ ತಗೊಂಡಿದ್ದೆ, ನೀವು ಹೊರಟೆ ತಗೊಂಡು ನಾನು ಹೊರಟೆ ತಗೊಳ್ಳಿ, ಕಾಂಪೌಂಡ್ ಆರ್ಗಾನಿಕ್ ಆಗಲಿ ಇನ್ಆರ್ಗಾನಿಕ್ ಆಗಲಿ ಅಥವಾ ಕೋಲೆಂಟ್ ಕಾಂಪೌಂಡ್ ಏನಾದರೂ ಆಗಿರಲಿ ನಮಗೆ ಆ ನೇಚರ್ ಬೇಕಾಗಿಲ್ಲ. ಸೊ ಡೆಲ್ಟಾ ಟಿಬಿ ಎಲಿವೇಶನ್ ಆಫ್ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಆಫ್ ದಿ ಸಾಲ್ವೆಂಟ್, ಇಟ್ ಇಸ್ mainly depends on number of solute ಅಥವಾ number of moles of solute particles. So that's why elevation of boiling point is taken as a qualitative property. So already we know that qualitative properties are those which are mainly depends on number of solute particles. According to our equation, delta TB is proportional to W2 by M2. Mass of solute divided by molar mass of solute. Mass of solute divided by molar mass of solute is nothing but number of moles of solute. Again, the delta TB is proportional to number of moles of solute. Therefore, the elevation of boiling point is a qualitative property. So that's about the concept. And again, this is a very important equation. That is for calculation. Calculation tumba important. Delta TB, elevation of boiling point. KB, endoscopic constant, that is given in the problem avare kodtane, and KB value for solvent, different solvent ke different value irutte. Iga water ge KB value different irutte, ether tagondre adakke different irutte, NHN tagondre adakke KB value jaasti irutte, andre different irutte. Totally KB is a function of nature of solvent. Solvent change adage KB value change aagta irutte, but one particular solvent ge KB is constant, adu yavade kandu change agalla. W2 mass of solute, M2 molar mass of solute, W1 is the mass of solvent. By using this formula, you can also calculate the molar mass of solute. So this is a very important equation. This is basically the problems na 3 marks. Okay na? Delta TB is equal to KB into W2 into 1000 divided by M2 into W1 in grams. KB value ಅವರೇ ಕೊಡ್ತಾರೆ, worry ಮಾಡಬೇಡಿ. So delta TB ಅಲ್ಲಿ ಕೆಲವೊಂದ್ಸಲ TB value ಕೊಟ್ಟಿರ್ತಾನೆ, ಕೆಲವೊಂದ್ಸಲ T0B ಕೊಟ್ಟಿರ್ತಾರೆ, ಅದು ನಿಮಗೆ ಗೊತ್ತಿರಬೇಕು. So delta TB is the TB minus T0B. That is TB minus T0B. TB minus T0B irutte. So TB is the boiling point of solution and T0B is the boiling point of pure solvent. So that's about the elevation of boiling point of solvent. So and also we can determine the KB value for particular solvent. And KB value ಕಂಡುಹಿಡಿಯಲು ಒಂದು particular equation ಇದೆ, but an equation derivation ಅಥವಾ ಏನಿಲ್ಲ, just direct equation ಕೊಟ್ಟಿದ್ದಾನೆ. So that is KB is equal to R into M1 into delta H, sorry, 1000 divided by W1 into delta H vaporization. So this is very important. So again KB value calculate ಮಾಡೋದಕ್ಕೆ, so KBR, that is gas constant, molar mass of the solvent M1, and W1 is the, so that is sorry, equation is before addition. That is KB is equal to R into M1 into T0B divided by 1000 into delta H of vaporization. Sorry for that. So here KB is equal to R, that is the gas constant. M1 is the molar mass of the solvent. T0B is the boiling point of pure solvent, and delta H vaporization, that is called as enthalpy of vaporization. Enthalpy of vaporization. So this is the one of the direct equation. Let's go in the NCERT textbook. So that is to calculate the KB for a given solvent. One solvent and put the KB value constant irutte, and find out modike is the equation. R value, that is gas constant value. M1, capital M1 is the Molar mass of solvent T0 is the boiling point of pure solvent. Delta H vaporization. ಯಾಕಂದ್ರೆ vaporization ಆಗ್ತಾ ಇರುತ್ತೆ. Boiling ಅಂದಾಗ vapors ಬರ್ತಾ ಇರುತ್ತೆ. That is enthalpy of vaporization. That is the equation to calculate Kb. So here in this elevation of boiling point concept, problems is very important. What is the unit of Kb? Kb unit ಅನ್ನು ಕೇಳ್ತಾರೆ and define Kb endoscopic constant define ಮಾಡಿ ಅಂತ ಕೇಳ್ತಾರೆ. ಒಂದು ಮಾರ್ಕ್ ಅಲ್ಲಿ ಸ್ವಲ್ಪ ಅಪ್ಲೈ ಲೆವೆಲ್ಗೆ ಹೋದಾಗ what happens the boiling point of solvent when we add non-molten solute in it? So that is increases. ನಿಮಗೆ ಗೊತ್ತಾಗಲಿಲ್ಲ ಅಂದ್ರೆ just remember the colligative property elevation of boiling point. Elevation ಅಂದ್ರೆ ಜಾಸ್ತಿ ಆಗ್ತಾ ಇರುತ್ತೆ. Vapor pressure ಏನಾಗ್ತಾ ಹೋಗುತ್ತೆ solute ಹಾಕಿದಾಗ that will be decreases. ಇಲ್ಲ ಅದನ್ನ ನೆನಪಿಟ್ಕೋಬಹುದು. Vapor pressure is inversely proportional to boiling point. When we add a solute into the solvent, definitely vapor pressure decreases and boiling point increases. And graphical representation ಗೊತ್ತಿರಬೇಕು. And delta T is equal to Kb in Pm. And again substitute the value of molarity. So molarity equation ಬರುತ್ತೆ. Substitute ಮಾಡಿ delta T equation ಬರುತ್ತೆ. So that's about the concept of elevation of boiling point of solvent. So based on this, so there are two important application questions are there. So one is seawater boils above 100 degrees Celsius. Seawater boils above 100 degrees Celsius. Give reason. That is a very question. That is based on elevation of boiling point of solvent. The first applied question, that is seawater boils above 100 degrees Celsius or 373 Kelvin. Give reason. Give reason. Remember, seawater is not a pure water. It consists of solutes. Number of salts are dissolved in the seawater. So therefore, that is acts as a solution. So as usual, so solution seawater consists of number of salts. Number of salts across solid and solutes ಇದೆ ಅಂದ್ರೆ what happens the vapor pressure? The vapor pressure will decreases, and what happens the boiling point? That will be increases. Pure solvent, pure water boils at 100 degrees Celsius. Adhe seawater since there is a presence of non-volatile solutes in the seawater, so therefore there is a solution. Adi solution allavage enagutte vapor pressure will be decreases and the boiling point increases. Hence in seawater the water boils above 100 degrees Celsius. So reason em baribekagutte because the seawater contains salts bracket alli bekadre non-volatile solutes. So therefore what happens? The vapor pressure of the seawater ಅಥವಾ solution ಏನಾಗುತ್ತೆ decreases, hence the boiling point increases. Therefore seawater boils above 100 degrees Celsius. So that is the one reason. So that is the one question. Second one is at hill region. In the hill region, water boils below 100 degrees Celsius. Below 100 degrees Celsius. Again give reason. So sea water above 100 degrees Celsius ಆಗುತ್ತೆ ಯಾಕಂದ್ರೆ solutes ಇರುತ್ತೆ. So therefore boiling vapor pressure ಕಡಿಮೆ ಆಗುತ್ತೆ, boiling point rise ಆಗುತ್ತೆ. So again hill region ಅಲ್ಲಿ water is boils below 100 degrees Celsius ಅಂದ್ರೆ 98 97 degrees Celsius ಗೆ boil ಆಗುತ್ತೆ. ಯಾಕೆಂದ್ರೆ in the hill region the atmospheric pressure is low. Atmospheric pressure is low or less. Atmospheric pressure ಏನಾಗಿರುತ್ತೆ ಕಡಿಮೆ ಇರುತ್ತೆ. So atmospheric pressure ಕಡಿಮೆ ಇದೆ ಅಂದಾಗ boiling point ಅಂದ್ರೇನು vapor pressure of the liquid become equal to the atmospheric pressure. But in the hill region ಮೇಲೆ ಹೋದಂಗೆ atmospheric pressure ಕಡಿಮೆ ಇರುತ್ತೆ. Atmospheric pressure ಕಡಿಮೆ ಇದ್ದಾಗ we can easily make the vapor pressure of the liquid equal to atmospheric pressure. ಒಂದು atmospheric pressure ಗೆ ಈಸಿಯಾಗಿ ಈಕ್ವಲ್ ಮಾಡಬಹುದು. ಆಗ ಅಲ್ಲಿ ಬೇಕಾದಂತ ಟೆಂಪರೇಚರ್ 100 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ ಬೇಕಾಗಿರಲ್ಲ. ಸೊ ಅದಕ್ಕಿಂತ ಕಡಿಮೆ 98 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ ಅಲ್ಲಿ ಏನಾಗುತ್ತೆ ಅಂದ್ರೆ ಆ ವೇಪರ್ ಪ್ರೆಷರ್ ಆಫ್ ವಾಟರ್ ಯಾಕೆ ಈಕ್ವಲ್ ಆಗಿರುತ್ತೆ ಅಟ್ಮಾಸ್ಫಿಯರ್ ಪ್ರೆಷರ್ ಈಕ್ವಲ್ ಆಗುತ್ತೆ. ಯಾಕೆಂದ್ರೆ ಹಿಲ್ ರೀಜನ್ ಅಟ್ಮಾಸ್ಫಿಯರ್ ಪ್ರೆಷರ್ ಏನಾಗಿದೆ ಕಡಿಮೆ ಇದ್ದಾಗ ವೇಪರ್ ಪ್ರೆಷರ್ ಇಸ್ ಈಸಿಲಿ ಈಕ್ವಲ್ ಟು ಅಟ್ಮಾಸ್ಫಿಯರ್ ಪ್ರೆಷರ್ ಅಟ್ ಲೋ ಟೆಂಪರೇಚರ್ ಅಂದ್ರೆ below 100 degrees Celsius ಏನಾಗುತ್ತೆ vapor pressure atmospheric pressure equal ಆಗುತ್ತೆ because in the hill region vapor pressure is low. Therefore at the hill region the water boils below 100 degrees Celsius. These are the applied questions. One mark ಅಲ್ಲಿ ಬೇಕಾದ್ರೆ ಕೇಳಬಹುದು ಇಲ್ಲ ಕಾಂಪಿಟಿಟಿವ್ ಎಕ್ಸಾಮ್ಸ್ ಅಲ್ಲಿ in the hill region water boils below 100 degrees Celsius because of ಕೆಳಗಡೆ ಆಪ್ಷನ್ ಕೊಡ್ತಾ ಹೋಗಬಹುದು ಅಥವಾ ಇಲ್ಲಿ the sea water boils above 100 degrees Celsius because of ಕೆಳಗಡೆ ಆಪ್ಷನ್ ಕೊಡಬಹುದು. So that's about the applied questions based on elevation of boiling point of solvent. So that is about the third colligative property, elevation of boiling point of solvent. And the last qualitative property, that is called as fourth one, depression of freezing point of solvent, or depression of freezing point. So that is taken as delta TF. Delta TF. Ali delta TB in the use of that is the body. F referred for freezing. So before that, what is the meaning of freezing point? See, freezing point and then so let me take a simple water here. So in the liquid state, here there is a water. So when we cool the temperature, water to freezing point is 0 degrees Celsius. That's liquid phase is converted into solid phase. Ice convert. So even in temperature, as the temperature decreases, when you come to 0 degrees Celsius, the liquid phase is converted into solid phase. Ice convert. This is the ice and solid phase. It is phase so the difference of two phase. That is water. So water phase is one solid phase. That is a liquid phase. That is liquid phase, and in that case here there is a solid phase. Okay. So in the substance water. So one particular temperature vapor pressure of that substance in which phase? Liquid phase. A substance to vapor pressure obviously liquid phase only, that is equal to vapor pressure of the substance in its solid phase. So that is freezing point is nothing but the temperature at which vapor pressure of the substance, which is the substance I am putting here, that is water, the vapor pressure of the substance in its liquid phase is equal to vapor pressure of the substance in its solid phase. One particular temperature now we can call it as freezing point of that solvent. That is, freezing point is the temperature at which vapor pressure of substance in its liquid phase is become equal to its vapor pressure become equal to vapor pressure in its solid phase. ಅಂದ್ರೆ liquid phase ಇದ್ದಾಗ vapor pressure ಏನಿರುತ್ತೆ ಆ vapor pressure ಮತ್ತೆ solid phase ಗೆ ಕನ್ವರ್ಟ್ ಆದಾಗ ಅಂದ್ರೆ ಅದೇನಂತ ಟೆಂಪರೇಚರ್ ಕಡಿಮೆ ಮಾಡ್ತೀವಿ ಫ್ರೀಸ್ ಆಗುತ್ತೆ. solid phase ಅಲ್ಲಿ ಬಂದಾಗ ಅದರಲ್ಲಿ ಚೆಕ್ ಮಾಡಿದಾಗ vapor pressure ಏನಾಗಿರಬೇಕು ಎರಡು ಈಕ್ವಲ್ ಆಗಬೇಕು. ಯಾವಾಗ ಯಾವುದೋ ಒಂದು ಪರ್ಟಿಕ್ಯುಲರ್ ಟೆಂಪರೇಚರ್ ಅಲ್ಲಿ vapor pressure substance in its liquid phase is equal to vapor pressure in its solid phase, that particular temperature is called as freezing point. So again at the same time, so let me take a simple example. So here there is a pure solvent again, pure solvent. So this is the pure solvent. So pure solvent and then freeze ಮಾಡ್ತಾ ಹೋಗ್ತೀವಿ. So freeze ಮಾಡ್ತಾ ಹೋದಾಗ that is converted into a solid, ice ಆಗಿ convert ಆಗ್ತಾ ಇರುತ್ತೆ. So ಯಾವ temperature ಅಲ್ಲಿ actually pure solvent ನಿಮಗೆ ವಾಟರ್ ನ ತಗೊಂಡಾಗ what is the water freezing point? That is about 0 degree Celsius. So 0 degree Celsius ಅಲ್ಲಿ ನಿಮಗೆ ಏನಾಗುತ್ತೆ, the pure solvent are converted into solid state, that is ice ಆಗಿ convert ಆಗುತ್ತೆ. That particular temperature is considered as a T0F. T0F is called as freezing point of pure solvent. This is called as freezing point of pure solvent. So ಈಗ ನಾನು ಏನು ಮಾಡ್ತೀನಿ, ಅದೇ solvent ಗೆ so I am going to add a non-volatile solute. Non-volatile solute. So when we add non-volatile solute into the solvent, what happens? That is become a solution. In that solution, again solute is there, again solvent is there. So ಮತ್ತೆ ಏನು ಮಾಡ್ತೀನಿ, ಟೆಂಪರೇಚರ್ ನ ಕೂಲ್ ಮಾಡ್ತಾ ಬರ್ತೀನಿ. ಸೊ ಟೆಂಪರೇಚರ್ ಕಡಿಮೆ ಮಾಡ್ತಾ ಬಂದಾಗ ಸೊಲ್ಯೂಷನ್ ಇರ್ತಕ್ಕಂಥ ಸಾಲ್ವೆಂಟ್ ಮತ್ತೆ ಏನಾಗುತ್ತೆ, ಫ್ರೀಸ್ ಆಗಿ ಸ್ಟಾರ್ಟ್ ಆಗುತ್ತೆ. ಬಟ್ ರಿಮೆಂಬರ್, ಸೊ ಆ ಒಂದು ಫ್ರೀಸ್ ಆದಾಗ ಆ ಟೆಂಪರೇಚರ್ ನ ಫ್ರೀಸ್ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. ದಟ್ ಇಸ್ ಕನ್ವರ್ಟೆಡ್ ಇಂಟು ಐಸ್. That temperature is considered as TF. What is TF here? So TF is the freezing point of solution. Freezing point of solution. So here pure solvent, freezing point T0F, freezing point of pure solvent, and solution, that is TF, freezing point of solution. So ಈಗ ನೀವು ಬೇಕಾಗಿರೋದು T0F ಜಾಸ್ತಿನಾ TF ಜಾಸ್ತಿನಾ, ಎಷ್ಟು ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಕಡಿಮೆ ಆಗುತ್ತಾ ಜಾಸ್ತಿ ಆಗುತ್ತಾ. ಸೊ ಅಲ್ಲಿ ನಿಮಗೆ ನಾನ್ volatile fluid ಹಾಕಿದಾಗ ಡೆಫಿನೆಟ್ಲಿ ದ ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಆಫ್ ದ ಸಾಲ್ವೆಂಟ್ ವಿಲ್ ಬಿ ಡಿಕ್ರೀಸಸ್. That is the meaning depression of freezing point of the solvent. So by adding non-volatile solute, what happens? The freezing point of solution decreases compared to solvent. Compared to pure solvent. ಅಂದ್ರೆ ಯಾವ ಜಾಸ್ತಿ ವ್ಯಾಲ್ಯೂ ಅಂತ ಗೊತ್ತಾಗುತ್ತೆ ನಿಮಗೆ. ಸೊ ಜಾಸ್ತಿ ವ್ಯಾಲ್ಯೂ ನಮಗೆ T0F ಇದೆ. ಸೊ ಲೆಟ್ ಮಿ ಟೇಕ್ ವಾಟರ್ ಆದಾಗ ವಾಟರ್ ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಎಷ್ಟು ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್. ನಾನ್ volatile fluid ಆದಾಗ ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಏನಾಗುತ್ತೆ? ಕಡಿಮೆ ಆಗುತ್ತೆ. ಬಿಕಾಸ್ ಯಾಕೆ ಕಡಿಮೆ ಆಗುತ್ತೆ ಅಂದ್ರೆ ವೇಪರ್ ಪ್ರೆಷರ್ ಆಫ್ ದ ಸೊಲ್ಯೂಷನ್ again decreases. ವೇಪರ್ ಪ್ರೆಷರ್ ಕಡಿಮೆ ಆಗುತ್ತೆ ಅಂದ್ರೆ the vapor pressure of the solution become equal to its solid state. Liquid state ಇರತಕ್ಕಂತ vapor pressure of solution ಅನ್ನ ಅದರ solid state vapor pressure ಗೆ equal ಮಾಡಬೇಕು ಅಂದಾಗ ನಾವು ಇನ್ನೂ ಟೆಂಪರೇಚರ್ ಏನು ಮಾಡಬೇಕು? ಕಡಿಮೆ ಮಾಡಬೇಕು. ಅಂದ್ರೆ 0 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ ಅಲ್ಲಿ ಅದು ಫ್ರೀಸ್ ಆಗೋದಿಲ್ಲ. ಸಲ್ಯೂಟ್ ಇರೋದ್ರಿಂದ vapor pressure ಕಡಿಮೆ ಆಗುತ್ತೆ. So therefore freezing point is decreases, that is about below 0 degree Celsius. Let me take, so that is about minus 1 degree Celsius ನ ಬಂತು ಅಂತ ಇಟ್ಕೊಳ್ಳೋಣ. 0 degree Celsius and minus 1 degree Celsius, which is higher. 0 is higher than roughly minus 1. So 0 degree Celsius is the freezing point of pure solvent. That is T0F. ಯಾವುದಕ್ಕಿಂತ ಜಾಸ್ತಿ ಇದೆ? That is freezing point of solution. ಅಂದ್ರೆ ಯಾವುದಕ್ಕಿಂತ ಜಾಸ್ತಿ ಆಗ್ತದೆ? ಸೊಲ್ಯೂಷನ್ ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಗಿಂತ ಸಾಲ್ವೆಂಟ್ ಪ್ಯೂರ್ ಸಾಲ್ವೆಂಟ್ ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಏನಾಗಿರುತ್ತೆ? ಜಾಸ್ತಿ ಇರುತ್ತೆ. ಸೊ ಟೋಟಲಿ ಏನಂದ್ರೆ ಅದೇ ಪ್ಯೂರ್ ಸಾಲ್ವೆಂಟ್ ಗೆ ನಾನ್ volatile fluid ಅನ್ನು ಹಾಕಿದಾಗ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಎಲಿವೇಟ್ ಆಗಿತ್ತು. So but ಇಲ್ಲಿ ಏನಾಗ್ತಾ ಇದೆ? freezing point is decreases. Reason ಏನಂದ್ರೆ the vapor pressure of the solution decreases. Therefore vapor pressure of the solution in its liquid phase equal to the vapor pressure of the same solution in its solid state at a low temperature. ಅಂದ್ರೆ freezing point of pure solvent ಗಿಂತ ಇನ್ನು ಕಡಿಮೆ ಟೆಂಪರೇಚರ್ ಗೆ ಬಂದಾಗ ಮಾತ್ರ ಏನಾಗುತ್ತೆ? ಇಲ್ಲಿರ್ತಕ್ಕಂಥ ಸಾಲ್ವೆಂಟ್ ಫ್ರೀಸ್ ಆಗುತ್ತೆ. ಸೊ therefore so ಅಲ್ಲಿಗೆ ಕಡಿಮೆ ಆಗ್ತಿದೆ ಅಂದಾಗ so vapor pressure the freezing point of the pure solvent is always higher than the freezing point of solution. Reverse case of boiling point. That's all. ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಗೆ ರಿವರ್ಸ್ ಆಗುತ್ತೆ. ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಏನಾಗುತ್ತೆ? ರೈಸ್ ಆಗುತ್ತೆ. ಎಲಿವೇಶನ್ ಆಫ್ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್. ಅದೇ ನಾನ್ volatile fluid ಸಾಲ್ವೆಂಟ್ ಗೆ ಆಗ್ತದೆ ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಏನಾಗ್ತಾ ಇದೆ? ಕಡಿಮೆ ಆಗ್ತಿದೆ. ದಟ್ ಈಸ್ ಕಾಲ್ಡ್ as depression of freezing point. Reason? Because by adding the non volatile solute, vapor pressure of the solution decreases, hence therefore vapor pressure of solution in its liquid state is equal to vapor pressure of the solution in its solid state at a low temperature. ಅಂದ್ರೆ ಪ್ಯೂರ್ ಸಾಲ್ವೆಂಟ್ ಗಿಂತ ಕಡಿಮೆ ಟೆಂಪರೇಚರ್ ಬರಬೇಕು. ಸೊ ಈ 0 ಗಿಂತ ಕಡಿಮೆ ಬರ್ತಾ ಇರುತ್ತೆ ಮೈನಸ್ ಲೆವೆಲ್ ಗೊತ್ತಾಗುತ್ತೆ. ಸೊ therefore that is Tf is the vapor pressure of solution freezing point of solution. T0F is the vapor freezing point of pure solvent. So therefore this is a higher value. T0F is greater than Tf. ಅಂದ್ರೆ solution freezing point ಏನಾಯ್ತು? ಕಡಿಮೆ ಆಯ್ತು. That is the meaning depression of freezing point of solvent. ಹಂಗಾದ್ರೆ ಎಷ್ಟು ಕಡಿಮೆ ಆಯ್ತು ಅಂತ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಕ್ಕೆ ಏನು ಮಾಡ್ತೀವಿ? So that can be taken as delta Tf is equal to ಏನ್ ಬರೀಬಹುದಂದ್ರೆ so T0F minus Tf. ಸೊ ಅಲ್ಲೇ ಬರ್ತಿದ್ವು TB minus T0 ಅಂತ ಬಂದಿದ್ವು. ಯಾಕಂದ್ರೆ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಆಫ್ ಸೊಲ್ಯೂಷನ್ ಜಾಸ್ತಿ ಇತ್ತು ಅವಾಗ TB minus T0 ಅಂತ ಬಂದಿದ್ವು. ಬಟ್ ಇಲ್ಲಿ ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಆಫ್ ದ ಸೊಲ್ಯೂಷನ್ ಕಡಿಮೆ ಇದೆ. ಸೊ therefore T0F minus ಪ್ಯೂರ್ ಸಾಲ್ವೆಂಟ್ ಗಿಂತ ಸೊಲ್ಯೂಷನ್ ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಜಾಸ್ತಿ ಇರೋದ್ರಿಂದ T0F minus Tf ಮಾಡಿದ್ರೆ ಎಷ್ಟು ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಕಡಿಮೆ ಆಗಿದೆ ಅಂತ ಕಂಡುಹಿಡಿಯಬಹುದು. ದಟ್ ಈಸ್ ದ ಮೀನಿಂಗ್ ಡೆಲ್ಟಾ Tf is equal to T0F minus Tf. So that is about the concept. So again that can be represented by using a graphical representation. So graph ಅನ್ನು ಯೂಸ್ ಮಾಡಿ ನಾವು ಏನು ಮಾಡಬಹುದು? ಅದನ್ನ representation ಮಾಡಬಹುದು. Same graph. So in the y axis I am going to take a vapor pressure, and at the y axis that is we are going to take the temperature in Kelvin. So Kelvin ನಲ್ಲಿ temperature ಅನ್ನು ತಗೊಂತಾ ಇದೀನಿ in the x axis. This is the y axis and this is x axis. So ಈಗ ನಾನು ಮತ್ತೆ ಫಸ್ಟ್ ಸಾಲ್ವೆಂಟ್ ತಗೊಂತೀನಿ. ಸಾಲ್ವೆಂಟ್ ತಗೊಳ್ಳೋದ್ರಲ್ಲಿ ಫ್ರೀಸಿಂಗ್ ಅಂತ ಹೇಳ್ತಾ ಇರೋದ್ರಿಂದ ನಾವು ಟೆಂಪರೇಚರ್ ರೈಸ್ ಮಾಡಾಕಿಲ್ಲ. ಟೆಂಪರೇಚರ್ ಏನು ಮಾಡ್ತಾ ಬರಬೇಕು? ಕಡಿಮೆ ಆಗ್ತಾ ಬರಬೇಕು. So as the temperature rises, vapor pressure increases. As the temperature decreases, vapor pressure goes on decreases. ಈಗ ಏನು ಮಾಡಬೇಕು? ಟೆಂಪರೇಚರ್ ಕಡಿಮೆ ಮಾಡ್ತಾ ಬರ್ತೀನಿ. So as the temperature decreases, vapor pressure also decreases. At that particular temperature, ಯಾವುದೋ ಒಂದು particular temperature ಅಲ್ಲಿ ನಾವು ಬರೀತಾ ಇರೋದು this is for solvent. This is for solvent. Solvent ಬರೀತಾ ಇದೀನಿ. So at this temperature, so this is for solvent. So now at this temperature what happens? The vapor pressure, this vapor pressure is equal to vapor pressure of the solvent and then water in its liquid phase become equal to vapor pressure in its solid phase. That is the temperature is called as freezing point. ಯಾವುದು solvent that is P0F. Freezing point of two solvent. ಮುಂದಾಗಿ ಕಂಟಿನ್ಯೂ ಆಯಿತು ಅಂತಂದ್ರೆ ಕಂಟಿನ್ಯೂ ಆಗ್ತಲೇ ಇರುತ್ತೆ. ಸೊ ವೇಪರ್ ಪ್ರೆಷರ್ ಗೋಸ್ ಆನ್ ಡಿಕ್ರೀಸಸ್. ಈ ಪಾಯಿಂಟ್ ಅಲ್ಲಿ ಏನಾಗಿದೆ ಸಾಲ್ವೆಂಟ್ ಫ್ರೀಸ್ ಆಗಿದೆ. ಫ್ರೀಸ್ ಆಗಿದೆ ಯಾವ ಟೆಂಪರೇಚರ್ ಯಾವ ಒಂದು ಸ್ಟೇಟಿಗೆ ಬಂದಿರುತ್ತೆ ಸಾಲಿಡ್ ಸ್ಟೇಟಿಗೆ ಬಂದಿರುತ್ತೆ. ಈ ಮುಂದಕ್ಕೆ ಏನು ಬರುತ್ತೆ ಅದೆಲ್ಲವೂ ಏನಾಗಿರುತ್ತೆ ಅಂದ್ರೆ ಫ್ರೋಜನ್ ಸಾಲ್ವೆಂಟ್ ಆಗಿರುತ್ತೆ. That solvent is frozen solvent. ಅಥವಾ ಏನಂತ ಕರಿತೀವಿ ಸಾಲಿಡ್ ಸಾಲ್ವೆಂಟ್ ಅಂತ ಕರಿತೀವಿ. ಅಂದ್ರೆ ಈ ಪರ್ಟಿಕ್ಯುಲರ್ ಟೆಂಪರೇಚರ್ ಅಲ್ಲಿ ವೇಪರ್ ಪ್ರೆಷರ್ ಆಫ್ ದ ಸಾಲ್ವೆಂಟ್ ಇನ್ ಲಿಕ್ವಿಡ್ ಸ್ಟೇಟ್ is equal to vapor pressure of the solvent in frozen state. Frozen state ಅಂದ್ರೆ solid state ಬಂದಿರುತ್ತೆ. ಸೊ ಇದು ಯಾವುದಕ್ಕೆ ಸಾಲ್ವೆಂಟ್ ಗಳಿಗೆ. ಈಗ ಸೊಲ್ಯೂಷನ್ ತಗೋಣ. When we add non-volatile solvent into the solvent, what happens to vapor pressure? That is decreases. ಈಗ ಆ ಸೊಲ್ಯೂಷನ್ ಅಲ್ಲಿ ಸಾಲ್ವೆಂಟ್ ಏನಾಗಬೇಕು ಫ್ರೀಸ್ ಆಗಬೇಕು ಅಂದ್ರೆ that is freezes at a very low temperature compared to the pure solvent. ಅದು ಸಹ ಬರೀತಾ ಬಂದಾಗ as the temperature decreases the vapor pressure goes on decreases. ಸೊ ಅದಕ್ಕಿಂತ ಇನ್ನೂ ಕಡಿಮೆ ಟೆಂಪರೇಚರ್ ನೋಡಿ ಇಲ್ಲೆಲ್ಲ ಒಂದು ಕಡೆ ಏನಾಗುತ್ತೆ. This is the particular temperature at which, so this is for solution. This is the particular temperature at which what happens? The vapor pressure of the solution in liquid state is equal to vapor pressure of the same solution in its frozen state. Frozen state solid state equivalent that is taken as TF. So ಈ ಟೆಂಪರೇಚರ್ ಅಲ್ಲಿ ಪ್ಯೂರ್ ಸಾಲ್ವೆಂಟ್ ಫ್ರೀಸ್ ಆಗ್ತಿದೆ. ಸೊ ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಏನಾಗಬೇಕು ಸೊಲ್ಯೂಷನ್ ಅಲ್ಲಿ ಕಡಿಮೆ ಆಗಬೇಕು. ನೋಡಿ ಇಲ್ಲಿ ಫ್ರೀಸ್ ಆಗ್ತಾ ಇದೆ, ಇಲ್ಲಿ ಫ್ರೀಸ್ ಆಗ್ತಾ ಇತ್ತು, T0F ಅಲ್ಲಿ ಸಾಲ್ವೆಂಟ್ ಫ್ರೀಸ್ ಆಗ್ತಿದೆ ಪ್ಯೂರ್ ಸಾಲ್ವೆಂಟ್. ಸೊ ಸೊಲ್ಯೂಷನ್ ಅಲ್ಲಿ ಏನಾಗ್ತಾ ಇದೆ ಅದಕ್ಕಿಂತ ಕಡಿಮೆ ಟೆಂಪರೇಚರ್ ಅಲ್ಲಿ ಫ್ರೀಸ್ ಆಗ್ತಾ ಇದೆ. So therefore, when you add non-volatile solvent into the solvent, what happens to freezing point? That is decreases. That is the meaning depression of freezing point. ಈಗ ಇವೆರಡರಲ್ಲಿ ಯಾವ ಜಾಸ್ತಿ ಅಂತ ಹೇಳಿದೆ T0F is higher compared to TF. So therefore, ಈಗ ಡಿಫರೆನ್ಸ್ ತಗೊಂಡಾಗ ನೋಡಿ this is the difference is called as delta TF. So ಅಂದ್ರೆ ಅಂತ ಬರೀಬಹುದು. So along the y axis x axis line the temperature ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. T0F is higher compared to TF. Therefore, delta TF is equal to T0F minus TF. ಇವೆರಡನ್ನು ಮೈನಸ್ ಮಾಡಿದಾಗ ಎಷ್ಟು ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಕಡಿಮೆ ಆಗಿದೆ ಅಂತ ಗೊತ್ತಾಗುತ್ತೆ. ಇದು ಪ್ಯೂರ್ ಸಾಲ್ವೆಂಟ್ ಸಲ್ಯೂಟ್ ಆದಾಗ ಏನಾಗಿದೆ ಸೊಲ್ಯೂಷನ್ ಆಗಿದೆ, ಅದು ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಕಡಿಮೆ ಆಯಿತು. ಎಷ್ಟು ಕಡಿಮೆ ಆಯಿತು ಅಂದ್ರೆ T0F minus TF ಮಾಡ್ಕೊಳ್ಳಿ ಎಷ್ಟು ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಕಡಿಮೆ ಆಗಿದೆ ಅಂತ ಗೊತ್ತಾಗುತ್ತೆ. ಸೊ ದಟ್ ಇಸ್ ದ ಈಕ್ವೇಷನ್ delta T is equal to T0 minus T0F minus TF, and this is the graphical representation for depression of freezing point of the solvent. So that's about the concept. It's very easy to remember. This is a complete reverse of boiling point elevation. Elevation of boiling point ಒಂದು ರಿವರ್ಸ್ ಬಂದ್ಬಿಟ್ರೆ ನಿಮ್ಗೆ ಈಸಿಯಾಗಿ ಗೊತ್ತಾಗ್ತಾ ಹೋಗುತ್ತೆ. ಸೊ ಅಗೇನ್ ಸೇಮ್ ಈಕ್ವೇಷನ್ಸ್ ಬರ್ತಾ ಹೋಗುತ್ತೆ. delta TB is equal to TB minus T0B. delta TF is equal to T0F minus TF. ಕಾನ್ಸೆಪ್ಟ್ ಗೊತ್ತಿರಲಿ. ನಾನ್ ವೋಲ್ಟೇಜ್ ಸೊಲ್ಯೂಟ್ ಅನ್ನ ಹಾಕಿದಾಗ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಎಲಿವೇಟ್ ಆಗುತ್ತೆ, ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಕಡಿಮೆ ಆಗುತ್ತೆ. ಸೊ ರೀಸನ್ is explained based on the vapor pressure. So next again, so continuation part of this one is for dilute solution. So in the study material ಅಲ್ಲಿ ಸ್ವಲ್ಪ ಸ್ಮಾಲ್ ಮಿಸ್ಟೇಕ್ ಆಗಿದೆ ನೋಡಿ. ಪೇಜ್ ನಂಬರ್ 39 ಆಗಿ ಈ ಗ್ರಾಫ್ ಅಲ್ಲಿ TF ಮತ್ತೆ T0F ಅಲ್ಲಿ ಏನಾಗಿದೆ ಅಂದ್ರೆ F ಬದಲಿಗೆ R ಅಂತ ಬಂದಿದೆ, ಸ್ಮಾಲ್ r ಬಂದಿದೆ. ಸ್ವಲ್ಪ ಕರೆಕ್ಟ್ ಮಾಡ್ಕೊಳ್ಳಿ. TR ಅಂತ ಬಂದಿದೆ ಅದನ್ನ TF ಮಾಡ್ಕೊಳ್ಳಿ. T0R ಅಂತ ಬಂದಿದೆ ಅದನ್ನ T0F ಮಾಡ್ಕೊಳ್ಳಿ. ಪೇಜ್ ನಂಬರ್ 39 ಸ್ಟಡಿ ಮೆಟೀರಿಯಲ್ ಅಲ್ಲಿ. So next continuation part of this depression of freezing point for dilute solutions. For dilute solutions, depression of freezing point of solvent, that is delta TF is proportional to molarity. Same thing as usual, delta TB is proportional to M ಅಂತ ಹೇಳಿದ್ದು ಅದೇ ರೀತಿ delta TF is proportional to molarity. So again proportionality constant delta TF is equal to KF into M. Again this is a very important equation called as equation number 1. Then what is KF? KF is the molar depression constant. Molar depression constant, but is also called as freezing point depression constant. Freezing point depression constant, or is also called as cryoscopic constant. Is also called as cryoscopic constant. So again, what is the unit? Define delta, sorry, KF. KF na define ಮಾಡಬೇಕು. So ಅಲ್ಲಿ KF na define ಮಾಡಬೇಕಾದ್ರೆ consider consider small m is equal to 1 molar. Just I am going to take a 1 molar solution. So as I explained in the previous example, that is derivation of boiling point express ಮಾಡಿದೀನಿ. So let me take 1 kg of solvent here, and to this I am going to add 1 mole of solute. When the 1 mole of solute is added to 1 kg of solvent, what happens to solution? Solution become 1 molar solution. The solution become 1 molar solution. Totally ನಮಗೆ ಗೊತ್ತಿರೋದು, when we add a non-volatile solute into the solvent, freezing point will be decreases. So ಈಗ ನಾನು ಏನು ಮಾಡ್ತಾ ಇದ್ದೀನಿ, 1 molar ಅಂತ ತಗೊಂಡಾಗ equation number 1 becomes delta TF is equal to KF. As in written as KF is equal to delta TF. So now I have to define the molar elevation depression constant. Molar depression constant is the depression of freezing point. Molar depression constant is the depression of freezing point observed when 1 mole of the solute dissolved in 1 kg of solvent. Kb define ಮಾಡಬೇಕಂದ್ರೆ ಅಂತ ಹೇಳಿದ್ರು. Kb is the elevation of boiling point of solvent when 1 mole of solute dissolved in 1 kg of solvent. Similarly, so depression of freezing point KF is the depression of freezing point, nothing but delta TF. Yavaga observe agutte when the 1 mole of solute dissolved in 1 kg of solvent is called as KF, that is freezing point depression constant or cryoscopic constant. That is, the freezing point depression constant is the depression of freezing point observed when 1 mole of non-volatile solute dissolved in 1 kg of solvent. Particularly 1 kg of solvent ಅಲ್ಲಿ 1 mole of solute dissolve ಮಾಡಿದಾಗ 100% depression freezing point ಏನಾಗುತ್ತೆ, ಡಿಪ್ರೆಷನ್ ಆಗುತ್ತೆ, ಅಂದ್ರೆ ಕಡಿಮೆ ಆಗುತ್ತೆ. ಆ ಎಷ್ಟು ಕಡಿಮೆ ಆಗುತ್ತೋ, particularly 1 mole ಅನ್ನ 1 kg of solute dissolve ಮಾಡಿದಾಗ ಎಷ್ಟು freezing point depression ಆಗುತ್ತೋ, that is itself a cryoscopic constant or molar elevation, sorry, molar depression constant. It can also be defined as ಇನ್ನೊಂದು ತರ ಡಿಫೈನ್ ಮಾಡಬಹುದು. So depression of KF is the depression of freezing point observed in 1 molar solution. Simple. 1 molar solution. Depression of freezing point observed with 1 molar solution. 1 molar solution is nothing but 1 molar solute dissolved in 1 kg of solvent. 1 kg of solvent ಅಲ್ಲಿ 1 mole solute dissolve ಮಾಡಿದಾಗ ಎಷ್ಟು freezing point ಕಡಿಮೆ ಆಗುತ್ತೋ, that is itself a molar depression constant. ಅದೇ ರೀತಿ 1 mole of solute ಅನ್ನು 1 kg solvent dissolve ಮಾಡಿದಾಗ ಎಷ್ಟು ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಎಲಿವೇಟ್ ಆಗುತ್ತೋ, that is called as molar elevation constant, that is Kb. So again, so there are the unit of KF. KF unit ಬರಿಬೇಕಾದ್ರೆ, so again ಬರಿಬೇಕಾದ್ರೆ ಏನು ಬರೀತೀವಿ ನೋಡಿ, KF delta TB, delta TF is equal to KF into M media. So therefore KF ಇಂದ ಏನು ಬರೀಬಹುದು, delta TF divided by M. So what is delta TF? Delta TF is the depression of freezing point. Freezing point is nothing but temperature. The unit of temperature is Kelvin divided by molarity. Again is barte mole per kg. So therefore the unit is Kelvin per kg ಮೇಲೆ ಏನಾಗುತ್ತೆ kg. So mole ಮೇಲೆ ಬಂದ್ರೆ per mole. Again there is the same unit, Kelvin kg per mole is the unit of KF, but is molar depression constant. As usual Kb को ಸಹ ನಿಮಗೆ ಏನಾಗುತ್ತೆ ಸೇಮ್ ಯೂನಿಟ್ ಬರುತ್ತೆ, Kelvin kg per mole. ಅಥವಾ ಏನಂತ ಬರೆಯಬಹುದು, Kelvin kg per mole also written as Kelvin per molar ಅಂತ ಬೇಕಾದ್ರೆ ಬರೆಯಬಹುದು. That is the unit of KF as well as the Kb. And one more thing, so that is we have to substitute the value of M. M is called as a molarity. So what is the molarity formula? That is W2 into 1000 divided by M2 into W1 in grams. So again M9 is substitute ಮಾಡ್ಕೊಂಡು ಹೋಗೋಣ. Equation 1 becomes delta TF is equal to KF into, so what is the M value, molarity, W2 into 1000 whole divided by M2 into W1 in grams. So that is the delta TF equation. So from this equation, by knowing the delta TF, depression of freezing point, KF is given value, ಅಂದ್ರೆ ಒಂದು ಕೆಲವೊಂದು solvent ಗೆ ಅದು particular value ಇರುತ್ತೆ. ಒಂದು solvent ಗೆ KF is constant, W2 is the mass of solute, W1 is the mass of solvent, M2 is the molar mass of solute. By knowing the Kf, delta T of W2 and W1, we can easily calculate the molar mass of solute. So molar mass of solute ಅನ್ನು easily calculate ಮಾಡಬಹುದು. Same equation delta T b ವಾಲೆ ಬಂದಿತ್ತು ನೋಡಿ, ಇಲ್ಲಿ Kf ಬದಿಯಲ್ಲಿ ಏನಿರುತ್ತೆ Kb ಇರುತ್ತೆ, ಇನ್ನು ರಿಮೈನಿಂಗ್ ಸೇಮ್ ಇರುತ್ತೆ. So delta T of ಬಗ್ಗೆ ಗೊತ್ತಿಲ್ಲ, delta Tf is equal to T naught F minus Tf. Delta Tb is equal to Tb minus T naught B. So totally, when we add non-volatile solute into the solvent, the boiling point is elevated and freezing point will be decreases. That is explained by using the reason of vapor pressure. So that is the equation to calculate the delta Tf. Or delta Tf ಗೊತ್ತಾಗಿದೆ ಅಂತಂದ್ರೆ Kf ಗೊತ್ತಿದೆ, W2 M1 ಗೊತ್ತಿದ್ರೆ we can easily calculate the molar mass of solute. So again, to calculate the Kf value for a given solvent, one the solvent Kf value constant. So that is a function of the nature of solvent. Solvent change after Kf value change after. So therefore Kf value can be calculated by using the formula, that is R into M1 into T naught F divided by 1000 into delta H of fusion. Delta H of fusion. So then Kb is equal to R into M1 into T naught B and that is the boiling point of pure solvent. 1000 into delta H of vaporization ಅಂತ ಬರಲಿದೆ. ಬಾಯ್ಲಿಂಗ್ ಅಂತ ಬಂದಾಗ ವೇಪರ್ಸ್ ಬರುತ್ತೆ, that's what is taken as enthalpy of vaporization. ಬಟ್ ಇದು ಫ್ಯೂಷನ್ ಅಂತ ಹೇಳ್ತಾ ಇದೀವಿ, ಫ್ಯೂಸ್ ಆಗುತ್ತೆ ಅಂದ್ರೆ ಫ್ರೀಸ್ ಆಗುತ್ತೆ ಅಂತ ಹೇಳ್ತಾ ಇದೀವಿ. ಡೆಲ್ಟಾ H ಫ್ಯೂಷನ್ FES ಅಂತ ಹೇಳಿದ್ರೆ enthalpy of fusion ಅಂತ ಹೇಳ್ತೀವಿ. Delta H fusion is nothing but enthalpy of fusion. So that is by using this formula we can actually calculate Kf. It's a gas constant. M1 is the molar mass of solvent. T naught F is the freezing point of pure solvent. Not under use ಮಾಡಿದ್ರೆ that is pure solvent ಅಂತ. 1000 into delta H of fusion, nothing but enthalpy of fusion. And remember Kf value is and Kb value. So both are constant for the given solvent. Solvent change ಆದರೆ ಮಾತ್ರ Kf and Kb value change ಆಗುತ್ತೆ ಹೊರತು ಅದು ಯಾವುದೇ ಕಾರಣಕ್ಕೂ ಬೇರೆ ಮೇಲೆ ಡಿಪೆಂಡ್ ಆಗೋದಿಲ್ಲ. Please remember ಇದು ನೆನಪಿಟ್ಕೊಳ್ಳಿ, ಕಾಂಪಿಟೇಟಿವ್ ಎಕ್ಸಾಮ್ಸ್ ಬೇಕಾಗುತ್ತೆ. Kf is and Kb value is constant for a given solvent. That is about the Kf. So that's about the concept of depression of freezing point of solvent. As usual, ಎರಡು ಸೇಮ್ ಬರುತ್ತೆ, boiling point as well as freezing point, just the reverse case ಅಷ್ಟೇ. So equations ಎಲ್ಲವೂ ಸೇಮ್ ಬರುತ್ತೆ, ಇದ್ರ ಮೇಲೆ ಪ್ರಾಬ್ಲಮ್ಸ್ ಕೇಳ್ತಾರೆ, ಅಲ್ಲಿ ಡೆಲ್ಟಾ Tb into Kb ಅಂತ ಇರುತ್ತೆ ಅಷ್ಟೇ, ಎಲ್ಲ ಸೇಮ್ ಇರುತ್ತೆ. So terms ನೆನಪಿರಲಿ, mass of solute, molar mass of solute, mass of solvent, abrasioscopy constant, and this is depression of freezing point. So that's about the depression of freezing point of solvent. So here one of the applied question, sea water freezes below 100 degrees Celsius. Sorry, below 0 degrees Celsius. Now the applied question, sea water freezes below 0 degrees Celsius. Give reason. Applied question. Because sea water is not a pure water, it consists of non-volatile solute. So therefore, sea water consists of non-volatile solutes, nothing but number of salts. So therefore, what happens to the vapor pressure of solution? The vapor pressure will be decreases, and the vapor pressure the boiling point increase ಆಗುತ್ತೆ, but freezing point will be decreases. So pure water ತಗೊಂಡಾಗ freezing point of pure water is 0 degrees Celsius. When we are going to add a non-volatile solute, nothing but sea water ಅಲ್ಲಿ solutes ಬಂದಿದೆ ಅಂತಂದಾಗ, so freezing point ಆ water ಏನಾಗುತ್ತೆ, sea water ಅಲ್ಲಿ ಇರ್ತಕ್ಕಂಥ water that is freezes below 0 degrees Celsius, because it consists of salts, nothing but non-volatile solute. Therefore, vapor pressure of sea water that will be decreases, hence the freezing point also decreases. What happens to the boiling point? Boiling point will be increases. So mainly reason happens in terms of non-volatile solute. When we add the non-volatile solutes or salts, so what happens to vapor pressure? That will be decreases. Therefore, the vapor pressure of solution in its solid state, in its liquid phase, become equal to the vapor pressure of the same solvent, same solution in its solid state require the low temperature. So therefore, the freezing point of water decreases in seawater. So therefore, seawater freezes below 0 degrees Celsius. The main reason is because it consists of salts, and therefore the vapor below seawater decreases, and the freezing point also decreases. That may be freezes below 0 degrees Celsius. For example, minus 0.5 degree or 1 degree, minus 1 degree Celsius and freeze out. That is the applied question based on the depression of freezing point of solvent. So that's about the 4 qualitative properties. That is RMPB, osmotic pressure, elevation of boiling point of solvent, depression of freezing point of solvent. In all the cases, there are 4 equations. All the 4 equations ಮೇಲ್ಮೇಲೆ ಏನಾಗಿದೆ ಪ್ರಾಬ್ಲಮ್ಸ್ ಇರುತ್ತೆ. ಆರ್ಡಿಯ ಪ್ರಾಬ್ಲಮ್ಸ್ ಒಂದು ಕ್ಲಿಯರ್ ಮಾಡಿದ್ದೀನಿ. That is RL ಮೇಲೆ ಪ್ರಾಬ್ಲಮ್ಸ್ ಆಗಿದೆ. And one more concept in the solution chapter, that is last concept, that is what is abnormal molar masses, and how the abnormal molar mass will of the solute will occur. So that is association of solute and dissociation of solute, and based on the association dissociation, so how the degree of dissociation and association will be explained by using Vanta factor. So and what are the value of Vanta factor for association and dissociation of solute, and that we have to discuss in the next class. And remember, so after the completion of that concept, abnormal molar mass mugidaga solution chapter close agutte. So after that, in more concept ಮೇಲೆ ನಿಮಗೆ ಪ್ರಾಬ್ಲಮ್ಸ್ ಇದೆ. That is osmotic pressure, elevation of boiling point, depression of freezing point. That will continue in the next class. Thank you.